examples for, sorry, I just got the recording message. Okay, excellent. And I will give you a couple of examples for why such analysis are interesting to consider. So I saw that there were a couple of talks today about LIGO inference. So this might be stuff that you've seen before and you're familiar with, but since I'm trying to explain it and give you like a different angle on the analysis and what we call flexible analysis, bear with me just for a moment. So usually when we have some gravitational wave data and we try to analyze it, what we do is we have some model for what we are measuring, either the signal that is astrophysical, like the gravitational wave from binary black hole, or something else is happening in the detector. And we usually label that H, because that's what gravitational waves are always labeled as H. We subtract this model from the data, and then whatever is left behind, we basically statistically check whether this is consistent with noise. This is the standard workflow of inference. And that H is some kind of model for what the detectors have observed. The standard workflow here makes no assumption requirement or what the models we're using are. The typical choice, and I'm assuming this is what was discussed earlier today and what people might be more familiar with, is what's called a template-based analysis, where the models for the signals are basically solutions to general relativity for compact binary mergers. So your H, your model, looks basically something like this. This is a typical waveform from two black holes merging, computed with your favorite methodology from numerical relativity to analytical calculations. The flexible analysis I will be describing is basically an extension of this, where instead of assuming that your signal or whatever you're observing is exactly a compact binary as described by general relativity, now your H, what you're observing, is something more flexible. Such an analysis is less sensitive because we no longer assume that we are observing compact binaries, but it is more flexible for situations where we're actually not 100% sure that the models for the signals we have are 100% accurate. So in this case, for example, what you can do is H, your model for your data, could be some sum of some basis functions W. There are different ways to pick W, and different types of basis functions make for different analysis, but what I will be talking about is a specific choice in an algorithm called Bayes-Wave, where the basis functions are signed Gaussian wavelets. So your signal, or H, now looks like a sum of functions that look like this form here, which is basically assigned Gaussian. It is given by this form, but if essentially think of it like a sinusoid that oscillates with an envelope that makes it decay. Okay, so this choice, of course, not unique. You can do different things, but this is what I will be talking about today. So then what happens is we basically follow the exact same steps as typical LIGO inference, where you have some model, it's described by some parameters, and you sample over those parameters with something like an MCMC, a Markov chain Monte Carlo, or any other sampling method that your heart is set at. And here's, for example, one sample from the posterior. In the top, you see the different wavelets colored with different colors. And there's 4 or 5 of them, I believe. Each of them individually looks nothing like a gravitational wave signal, right? It doesn't look like a binary black hole merger, but when you sum them at the bottom, that looks like a typical binary black hole gravitational wave signal. And that indeed was GW150914. Now, so the various parameters are sampled over the same way you sample over, say, the masses of a binary black hole or the spins of a binary black hole. But the elephant in the room is actually, how many of these are you using? What are you doing about this? This summation is a finite summation, of course. How do you choose how many of those of those basis functions of those wavelets to use. And the way this is done is basically by, again, marginalizing or sampling. This also allows you to avoid overfitting, to not fit too much of the noise. The number of wavelets, rather than fixed a priori by the analyst, the user, is again sampled over, same way the masses are sampled over. So for example, if you have run something like an MCMC or a nested sampling before and looked at the posterior distribution for the mass of a black hole, you will probably have seen plots like this, where the top is a histogram, while the bottom is each sample plotted. And this is an example for the mass of one of the gravitational wave events we have detected. In this case, when you are having the number of wavelets, you can think of it as basically doing the exact same steps, but rather than a continuous variable, like the mass of a black hole, you instead have a discrete variable, where you basically changes in discrete numbers. So you have either 1 or 2 or 3, and then you do basically the entire workflow, same as before with your Markov chain Monte Carlo. So these are the plots on the right, where you can see at the bottom right, again, the chain, instead of a continuous variable, you have a discrete variable. So when all is said and done, you put everything together, you analyze the latest interesting gravitational wave signal the detectors have observed, and you can get plots like this. So this is, I believe that this is 170104, discovered quite a long time ago now. And you can see the data in the two detectors in Hanford and Livingston. And with the shaded regions, you can find the posterior for our reconstruction, what we think the signal that was observed that day was. In the blue, it's the standard analysis you get when you assume it's a binary black hole. So think solutions to GR in terms of the EOB waveforms or the phenom waveforms. You analyze the signal, you get the blue. Well, the orange is the more flexible wavelets analysis I have been describing. And you can compare the two and see some features of the analysis. First of all, you see that they agree, so that's good. The flexible analysis agrees with the analysis that assumes general relativity, so that's a good first step, that we know what we're doing. But you can also see other things. For example, the agreement is strongest where the signal is strongest, as expected. But the orange analysis has larger uncertainties. That makes sense because we have a sort of weaker prior, we have a weaker model for the signal. We're not as sure about what the signal should look like. So our error bars are larger. This is expected. But also, as you go further back in time or further back in frequency of the signal, you start seeing disagreements between the two. This is also expected because the generic analysis needs to really see a signal, needs to be able to see a signal on top of the noise in order to reconstruct it. While for a binary black hole, what you usually do is you see the signal where it's really strong, and then you extrapolate back at earlier times and lower frequencies. So you can track the signal a little bit better as you go back in time. Okay, so this is a sort of generic introduction, and I will give you two examples for why this sort of analysis is interesting beyond just comparing, like this plot I'm showing here, to the standard analysis that assumes general relativity. The first example I will describe is signal polarizations. We know that gravitational waves in general relativity have two polarizations. GR predicts only two propagating degrees of freedom, the famous plus and cross polarizations. And we basically, in terms of measuring them, their defining characteristic is how the detectors respond to them. So the plot on the right shows you basically the response of an interferometric 90-degree detector to the two different polarizations. So what we see is basically a linear combination of the two of them. This is the equation at the center of the page, where what a detector sees is a combination of the two polarizations that arrive in the detector coupled to how the detector responds to each polarization. These are the Fs. And those Fs are very well understood. We can write them down in literally one line. So we can compute what the detectors see. But if you want to measure these independently and understand what the polarization of the signal is, you have 2 degrees of freedom to measure, which means you need at least 2 detectors. You can't measure polarizations with 1 detector. You can barely do it with 2 with Hanford and Livingston, because Hanford and Livingston are pretty much co-aligned with each other. They are off by about 10 degrees. So they sort of see the same polarization. They don't see independent polarizations. So you need as many detectors as possible to see those polarizations. So what are those polarizations? For a compact binary, the usual plus and cross polarizations are given in the frame we usually use, are given by expressions like the ones on the right. And what you see basically depends on the inclination with which you're observing the signal. So if you see a signal face on, like look up in the sky where look at the source. And if you see it face on, basically, if you look up at the sky, you see 2 black holes moving in a circle, then you see equal amounts of both the plus and the cross polarization, and that's the strongest emission. Well, if you see the signal sort of edge on, like 90 degrees angle between the orbit, the normal to the orbit and the line of sight, then you basically lose one of the polarizations. You lose the cross polarization, you only see the plus, and that's where the emission from the signal is weakest. Okay, so this is a general picture about polarizations. So let's try to see how we can extract them from gravitational wave data. And the simplest thing to do is assume that signals are elliptically polarized. This is a pretty good approximation. It might sound a bit too restrictive, but it's actually not. In this case, your plus polarization is something generic. In this case, I've written it as a sum of wavelets. And the cross polarization is basically a phase-shifted plus polarization. This is a definition of elliptical polarization, essentially, where you have some parameter linking the plus and the cross polarization that is constant. So you basically have a constant rescaling between plus and cross. If this parameter is 0, the ellipticity is 0, then you're in the case what we call linear polarization. You have only one of the 2 polarization modes. But if it's 1, you basically have equal amounts of plus and cross. So that's what you call a circular polarization. In between, where epsilon is neither 0 nor 1, then you have elliptical polarization. And that's pretty much consistent with almost everything we've seen so far. So definitely everything from the second observing run, and the vast majority of signals from the third observing run were elliptically polarized, or at least to the best of our understanding, to think how well we can measure them. And then the signals look like this, basically. It's the standard binary black hole signal you have in your mind with the increasing amplitude, increasing frequency. These are elliptically polarized. If you want to go a step beyond, and you don't want to assume elliptical polarization, but you have something more generic, then of course you have to have a more generic model for your signal where both plus and cross can vary almost independent of each other. They have to have some common characteristics, like the frequency evolution of the signal is basically dictated by the source. It's not dictated by how the detectors are oriented. So that the time frequency content of the signal is not free to be completely independent between plus and cross, right? Because they have a common origin. But this is sort of the case where you have more complicated, more interesting signals. Here's an example of such a signal. If you have spin precession, high order modes, or something that's actually not a compact binary, like a supernova or a random burst of gravitational waves, there's no a priori reason to expect that those are circularly polarized. And in fact, what polarization those signals carry, once we see a signal like this, what kind of polarization they carry, could be interesting information about them. So here's an example for how this works with a simulated signal. For this, I'm showing spin precession as an example of a phenomenon that breaks elliptical polarization. And the precessing signal is on the bottom right, while a non-precessing signal, so elliptically polarized, is on the left. And you can kind of see the differences. The one on the right has more interesting features with its amplitude and frequency modulations. And then you can see that if you assume that's elliptically polarized, you're not going to extract it very well. You're going to bias yourself and your parameters, but you can extract it much better by allowing it to have a more generic polarization. And most interestingly, if we see a signal like that, we can start putting some constraints on what is its polarizations, what the polarization state is. In electromagnetism, the usual way we do this with is the so-called Stokes parameters. You can do similar things with gravitational waves. So here's an example of the so-called U-Stokes parameter, which is a combination of the plus and the cross polarizations of the signal. And you see a plot here of the Stokes parameter as a function of frequency. So given a specific signal, plot the Stokes parameter as a function of frequency. For different kinds of signals, and that the dashed lines are the true value for a simulated signal, and these shaded colored regions are what we extract for it. So if your signal is actually elliptically polarized, something like the green, it's the Stokes parameter is 0, and you extract that. You say, well, this signal had a 0 ellipticity and it was constant. But if you have something more interesting, like the red or the purple, we can extract it. This example is for spin precession. And in reality, if we see a precessing signal, like a strongly precessing signal, we're not going to use something like that to extract its polarization. We're going to do it with something like the EOB or the phenom waveform models. But this is just an example for what we can do when we have something like that is not a compact binary. If we see a signal that is more complicated, and that is a way to extract its polarization. Going one step further, I said that general relativity predicts 2 polarization modes, but beyond GR gravities, metric theories of gravity can have up to 6. And again, the defining characteristic of all those, as far as measurement is concerned, the defining characteristic of all those modes are the plots on the right that show again how a detector like LIGO responds to each of the polarization states. To this day, we haven't found any beyond GR polarization or any deviation from GR to begin with. But we keep looking, and the thing I would like to get across is that this measurement is similar to measuring the sky localization of your source. If you have 2 detectors, you're not going to have as good constraints. You need at least 3 or 4 or as many detectors as possible to do this kind of measurement. There's many examples in the literature with alternative theories of gravity that predict some kind of extra polarization between plus and cross. Here's an example. Of course, we don't have any self-consistent model for a spiral merger ring down with extra polarizations, but we have some examples for things to look at. So in this case, what we're going to do is we're going to extend our analysis. Instead of the first equation, what you observe, instead of a linear combination of plus and cross, you actually also add something additional. In this case, that would be a scalar mode, one of the additional possible modes that GR doesn't excite, but beyond GR theories might. And in this case, H plus, H cross, and HB, which is the scalar mode in your signal, are again described generically by wavelets. Those wavelets now can have different time frequency content. Actually, if you look at examples from high energy extensions to GR that predicts alternative polarizations, the time frequency content of the tensor versus the time frequency content of the scalar mode are not the same. So you actually have to have completely independent time frequency evolution for your signal. And I'm going to show you a couple of examples for how this can work. This is for a real event that was observed almost 2 years ago now, I guess, GW 190521, the heaviest expanded black hole. And we analyze it with this model, not detect any additional polarizations beyond the 2 tensor ones, but we can put an upper limit on the SNR, and the green and orange curves are an upper limit on the signal to noise ratio of beyond GR polarizations. And we can place upper limits on how much non-GR polarization content this signal had. Going one step further, we have not seen a deviation, But that doesn't stop us from exploring what happens if we see a deviation. Here's a quite egregious, actually, deviation from GR, simulated, nobody panic. But here's a signal, it's a simulated signal that has a basically, you can sort of see that it looks, is that a 1? Oh, 10. Okay, thank you. I panicked for a little bit. Okay, great, thank you.
Sorry for that.
No worries. Okay, so here's, you kind of see it looks a bit like a merger, but then there's a burst kind of close to merger. So you have a ramp up of frequency and there is a burst. That burst is maybe some scalar power that comes out of the binary during merger. And we can analyze it in this example using 4 detectors, and the blue is the full data, how you reconstruct the full data. But then you can also split how much is scalar. You see the scalar is basically a burst of radiation. Is there an additional?
Sorry, this includes the discussion.
Oh, okay, thank you. Okay, so the orange is the beyond GR part, and the green plotted here would be the GR part. So the green looks like a typical merger, but then in this case, we have identified that something additional has happened at merger. So if we see something like that, we will be able to identify it. So I'm gonna then skip that and go to my second example for how flexible analysis are interesting. And it has to do with detector glitches. We're not even talking about signals now. We're actually talking about detector glitches. Glitches happen in the detector, unfortunately, more often in the detectors, unfortunately more often than we would like. And sometimes they overlap with signals. Famously, this happened back with 170817, the first binary neutron star. You might have seen the plots on the left, with the signal being the very nice chirp, and a huge glitch, a very loud glitch, happening about a second, slightly less than a second before merger. That was a huge glitch, actually. It was one of the really loud ones with a signal to noise ratio, I think around 800 or 900. In this case, what we did, you see at the bottom, this is the strain data. And we basically, again, modeled the glitch now, not the signal. We modeled the glitch now as a sum of wavelets. And when we do that, we can subtract it and remove it from the data. You see the middle plot here on the right is the same data as before, but where the glitch has been removed. And now you see the signal. And in that case, for 170817, we checked quite extensively that this was a safe thing to do. It was an okay procedure. We did that by simulated signals, looking at other examples of really loud glitches, added fake signals on top of them, simulated signals, and measured their parameters, see that we can do things accurately. We can remove the glitch and then measure the parameters. So that gives us confidence that for 170817, the glitch subtraction procedure was safe, and we actually got the correct parameters for the signal. But going forward, you might think that this was an unlucky instance, but actually it might not be. In 03, the third observing round, at least the first half of it, the glitch rate increased by quite a bit in the 2 LIGO detectors, while it was decreased in Virgo. But in the 2 LIGO detectors, they're at the point of about slightly less than a glitch per minute. And if you recall that neutron star binaries last for 2 minutes, and you have a glitch per minute, most likely the next binary neutron star will also overlap with a glitch. And we have to figure out what to do with that. We have to continue developing ways to deal with those glitches. In the 170817 case, we were kind of lucky, because if you look at this, the signal and the glitch look very different, right? The signal is very long, 2 minutes. The glitch is very, very well localized. We won't always be so lucky. Here's an example of a binary black hole with a glitch. The purple is the binary black hole. The yellow is the glitch, and they look a lot more similar. At this point, it's more difficult to tell them apart. So what the final thing I'm going to talk about is an analysis to actually separate them, where you simultaneously look at the signal and the glitch. Well, the signal is modeled as a binary black hole. Thank you. As a binary black hole. So the signal is modeled like what you expect with something like a phenome model. The glitch is the sum of wavelets, and you model them at the same time. So here's an example in the Hanford and Livingston detectors, where you have a glitch in Livingston, that's the purple, and a signal in both of them, and you model them at the same time. And I'm going to show you a couple of examples for how well this works. This is a so-called blip glitch. It really throws off searches for binary black holes. But here's how you can separate. If a binary black hole happens at the same time as a blip glitch, in the two examples showing at the plot here, you can separate them, the orange and the blue, and extract the parameters. And of course, you can subtract it from the data. Look at, so in this plot, if you look at the top left and top right, basically the top left includes both a glitch and a chirp, a nice pretty chirp. And on the right, we have removed the glitch and you just have the chirp, which is what you want. You just need your signal and no extra stuff on top. I have a couple more examples for how well this works for other types of glitches. Here's another example of a scattered light glitch that has been removed from the data and you only have the chirp left behind. This is how it will work for 170817. Indeed, 170817, that one glitch was quite massive. If you look at the plot below, it's basically an 150 sigma deviation from the noise. It was quite a big glitch, much bigger than most of the ones we have to deal with. But anyway, this is the second example I wanted to talk about. And I will take any questions, leave with my conclusions that flexible analysis are interesting because they can both help you analyze unmodeled signals like polarizations beyond GR polarizations, but also support standard analysis like subtract glitches from data because you don't want the glitches, you just want the signal. And I'll take any questions. Thank you.
Thank you very much for the nice talk. And we shall take questions. And I am looking for raised hands. Is there any question?
There are a few raised hands in the chat, and I'm the first one, Luc. So if you may,
okay.
I may start.
Very good. Please ask your question.
I'd like to thank again Katerina for making this presentation on the fly. Katerina, you said something that struck my attention earlier about the polarization due to scalar mode and the fact that their time frequency content may be very different than the other mode. I think I understood that right.
That's right.
I'm surprised because I would have guessed that you would still have a very intimate correlation between the gravitational wave being emitted and the mass distribution. So what is the physical reasoning for this? And what does the gravitational wave from the scalar mode brings in terms of information?
Yeah, so I'm gonna describe how this goes for this example. This is Brandstad theory, and those expressions have been calculated. So to leading order, the plus and cross are the frequency or the phase is twice the orbital phase, right? So this is the cosine 2 phi sine 2 phi. So you're exactly right that the same sort of generation process and the same binary motion generates the scalar mode, but the harmonics are not the same. So the scalar mode in this case, it's represented by this S bar. S bar is actually a huge expression that I just removed. This S bar is a combination of a term that goes as twice the orbital phase, plus a term that goes as once the orbital phase, plus constant. So it's actually, if you combine all these together, and that's at leading order, right? So at higher order, you have a lot more things, even at plus and cross. But at scalar, even at leading order, you have combinations, different combinations of harmonics of the orbital phase. That's why overall, when you add all those harmonics, it doesn't look the same as the tensor evolution.
Okay. I think that clarifies. Thank you.
Thanks. Our next question is by Guillaume.
Yes, it's maybe a strange question, but most of the glitches you showed, except the scattered light, I think, were almost time symmetric. So I was wondering if it's just an effect of selection of the examples you wanted to show us, or is it the case in real life? And if yes, why?
So a lot of those glitches are basically some excitation in the detector that then decays away, right? And excitations in general, in systems, mechanical or otherwise, excitations look a certain way. They look like decaying sinusoids. So in many cases, those will end up being symmetric, but not always. So blip glitches are kind of symmetric, but short duration. So they look like a very heavy binder black hole. This is why blip glitches are very, in quotes, popular. They're being studied a lot because they are problematic. So maybe the selection effect here is that this thing looks like a gravitational wave signal, like a very heavy gravitational wave signal. They also have an unknown origin, most of them. So they're particularly problematic. So if there is a selection effect for blip glitches, I would say it's this, that they're actually problematic. Scattered light, the selection effect, why it's chosen is that it became very common in Livingston during 03A. So this is why it's shown. So the selection effect for what glitches are shown here are the most common ones, or the most problematic ones for actual analysis. If you have a glitch that happens once a year, it probably won't overlap with a signal. You don't care as much about it.
Thank you.
Mm-hmm.
Okay. Another question? Concerning the wave polarizations, with the flexible method that you described, would it be possible to do better than just checking pure tensor case versus pure scalar polarization or pure vector polarization, which is not very realistic? Is it possible to check for a mixture between tensor and scalar modes, for instance?
Exactly. So this is the goal. So this example here for 1905-21 is exactly what you're describing. When you have a mixed content, where you have tensor plus something else, and you put an upper limit on the plus something else. Of course, the upper limits are not going to be as strong as if you assume it's completely scalar or completely vector. But this is because you have, when you assume pure modes, you have assumed a very extreme deviation from GR, and you can really rule it out. We know that tensor modes exist, right?
Yes.
Yeah.
Thank you very much.
Mm-hmm.
So I see a comment on the chat by Didier Bertint. Is it a question or a remark for the speaker?
No, it was just a remark about the previous question. To say that maybe the symmetry in the time frequency plot is linked to the way they are done.
Okay, thank you very much. So we thank Katerina again.
Thank you.
There is another question, Luc.
Okay.
Alexandre Toubiana has a question for Katerina.
Yes, please, go on.
Yes, thank you. Thank you very much for the very nice talk. I have a question concerning something you discussed at the very beginning when you showed how to reconstruct the first event with wavelets. And you say that when you go back in the early spiral, I think it was, yeah, exactly. So you were saying that you're getting out of phase in the early spiral because you need to see the signal in order to reconstruct it. So how exactly can we use this technique to reconstruct non-chirping signals? So I'm thinking, for instance, of systems that we might see in the Lisa band, or even to some extent binary neutron stars, which are chirping, but we don't see the merger.
Right. So if you have something like 170817, where, I mean, this is a plot of 170817 that, look at the top in Hanford. It's constant, like 0.1 sigma away from the noise, right? In this case, you can barely extract it with this method. You need things that are on top of the noise with this method. So something like 170817, you can basically, I don't remember, you can extract maybe like less than 50% of the signal to noise ratio, I'd have to go back and check runs. But if it's something really below the noise, you cannot extract it. You need something above the noise, because you don't assume the nice phase coherence you have for binary black holes. And for a signal like 170817, it's this that brings you on top of the noise, and you have a detection. So when you don't assume that, then you cannot see things that are really below the noise level. For LISA, again, it will depend on what kind of signal we're talking about. If you're talking about a massive black hole binary, then you can see that. You can see it with any analysis. So I guess what kind of signal exactly do you have in mind?
I was thinking more of stellar mass binaries in LISA or galactic binaries, but then I guess it's more similar to the case of binary neutron stars.
Yeah, exactly. So stellar binaries definitely, I would say, it's more similar to neutron star binaries. Galactic binaries depends if they're resolvable or not. But again, in those cases, for those kind of systems, we have pretty good models for them, right?
Yes. Yeah. Okay. Thank you very much.
We're going to see them. Yeah.
Okay. Thank you very much. I think that there are no other questions, and we thank you again.
Thank you.
And our next speaker